Today we will study IR and FTIR spectroscopy. IR spectroscopy is also known as vibrational spectroscopy because IR radiation cause vibrations in the molecule. They cause vibrational transitions in the molecule. IR radiations are not energetic that they cause electronic transition. So only vibrational transitions is produced. The vibration in IR spectroscopy is known as fundamental vibrations. IR spectrum is mainly used in structural elucidation. We use IR spectrum for determining the structure of organic compounds and to determine the functional groups which is present in organic compounds. The infrared region of spectrum encompasses radiation with wave number ranging from 12,800 to 10 per centimeter. This is the wave number range of IR region. IR region is divided into three parts: near IR region, middle IR region and far IR region. Near IR region means this region is near to visible region. So near IR region wavelength is from 0.78 to 25 micrometer. Middle IR wavelength range is 2.5 to 50 micrometer and far IR wavelength range is 50 to 1000 micrometer. And here are the wave number values: near IR 12,800 to 4,000 per centimeter, middle IR 4,000 to 200 per centimeter wave number, and far IR are least energetic 200 to 10 per centimeter. Most of the analytical applications are confined to the middle IR region. Why in the middle IR region? Because absorption of organic molecules are high in this region. Most of the molecules absorb middle IR region. In a molecules, atom or group of atoms are connected by bonds which are similar to springs and not rigid in nature. These are the two atoms which are connected by bonds. These atoms are continuously vibrating like they are connected by a spring. Mean atoms in a molecule are not stationary, they are always vibrating. This characteristic vibration are called natural frequency of vibration. So each atom, each molecule has some natural frequency of vibration. Different molecules, different type of bonds are vibrating with different frequency. Here is vibration of diatomic molecule approximate and isolating spring. Two molecules, two atoms are connected in a molecules. They will vibrate. When energy in the form of infrared region is applied, then it causes a vibration between the atoms of the molecules. Mean the atoms in a molecule are already vibrating, but when IR radiation is absorbed, their vibration become more fast. Their vibrational transition take place by absorption of IR radiation. And when IR radiation is absorbed, when applied infrared IR frequency, vibration is equal to natural frequency of the molecule, then absorption of IR radiation take place. If the natural frequency of the vibration of the molecule it matches with the frequency of IR radiation, both frequency are matched, then this type of IR radiation will be absorbed by the molecule. And in IR spectrometers, a peak in the spectrum will be obtained. We will see in the later slides the IR spectrum and the peaks in that spectrum which are due to absorption of radiation. IR radiation. Different functional group absorb characteristic frequencies of IR radiation. For example, hydroxyl functional group will absorb different frequency of IR radiation. Ketonic functional group will absorb different frequency of IR radiation. So peaks for each functional groups are formed at different frequency regions in the spectrum and hence give the characteristic peak value. Mean each functional group will have a different peak at different different intensity of the peak at different frequency. Therefore, IR spectrum of a chemical substance is a fingerprint of the molecule for its identification. IR spectrum is a characteristic of the molecule. It is a fingerprint of the molecule, and a molecule can be identified by its IR spectrum. Mean IR spectrum of each molecule is unique. Like the fingerprints of persons are unique, the IR spectrum of each molecule is unique. Criteria for a compound to absorb IR radiation. There are two criteria: correct wavelength of radiation. If there is correct wavelength of radiation, it will be absorbed, and if it change the dipole moment of the molecule, that IR radiation will be absorbed by the molecule. Correct wavelength of radiation. A molecule to absorb IR radiation, the natural frequency of vibration of some part of the molecule is the same as the frequency of incident radiation. So if two frequencies are matching to each other, then IR radiation will be absorbed by the molecule. And the second criteria is change in dipole moment. A molecule can only absorb IR radiation when its absorption causes a change in its electric dipole. Dipole, one part of the molecule partially positive, other part of the molecule partial negative. So IR radiation will only be absorbed when after absorption there is change in dipole moment of the molecule. A molecule is said to have electric because when vibrations are changed, dipole moment is changed. A molecule is said to have an electric dipole when there is slight positive and slight negative charge on its components of atom. For example, in hydroxyl group there is dipole moment. Oxygen is partial negative, hydrogen is partial positive. When IR radiation is absorbed by OH group, change in its dipole moment takes place. Dipole moment value is changed to some extent. Here is the IR spectrum. For isopropyl alcohol, this IR spectrum is for isopropyl alcohol, CH3 whole twice OH. The infrared absorption bands identify the various functional groups of the molecule. So here different peaks are obtained. On the y-axis is transmittance of IR radiation percentage in the form of percentage, and on the x-axis is the wave number of IR radiations. So different peaks are obtained, and each peak show the mode of vibration by some functional groups. For example, this peak at this wave number, this peak is showing the stretching vibration of hydroxyl group. This second peak is showing the stretching vibration of CH. In this wave number 3000, IR radiation are absorbed by this CH group, and its stretching vibration is transition in its stretching vibration takes place. And here are the peaks for other functional groups, and there are different peaks for different types of vibration, because vibrations are of different types. Vibration may be stretching, it may be bending. So each IR spectrum for a molecule is the fingerprint. Isopropyl alcohol always will have this type of spectrum. The peaks would be obtained at the same wave number values, and due to this unique spectrum, molecules can be identified by IR spectroscopy. Okay, here molecules are vibrating, and there are different types of molecular vibration: stretching vibration, and there are two main types of vibration: stretching vibration and bending vibration. Stretching vibration, like the vibration of the spring, sometime it elongates, sometime it stretch. Vibration or oscillation along the line of bond. along the line of bond. Means two molecules, the distance between them is, suppose this distance is increased and decreased like this. Sometimes distance is increased and sometimes distance is decreased. This type of vibration, which is along the line of bond, this type of vibration is called stretching vibration. Due to stretching vibration, there is change in bond length. Sometimes bond length is short, sometimes bond length is long. Occurs at higher energy, 400 to 1250 per centimeter. Mean when IR radiation of this wave number are absorbed, then stretching vibration in the molecule, transition in stretching vibration of the molecule take place. There are two types of stretching vibration: symmetrical stretching vibration and asymmetrical stretching vibration. Symmetric stretching vibration. Two bonds increase or decrease in length simultaneously. Carbon and hydrogen, they stretch simultaneously. These two bonds stretch simultaneously. They elongate simultaneously. This is called symmetric stretching. And asymmetric stretching, in this one bond length is increased and other is decreased. Mean this length decreases and at the same time this bond length increases. This is called asymmetric stretching vibration. And second type of vibration is bending vibration. Vibration or oscillation not along the line of bond. They are also called as deformation. In this, bond angle is altered. Bond length is not changed, but bond angle is altered. And the wave number of IR radiation at which this type of vibration takes place, it is between 1400 to 66 per centimeter. There are two types of bending vibration: in-plane bending vibration and out-plane. An in-plane bending vibration have two types: scissoring and rocking vibration. Out-plane bending vibration have also two types: wagging and twisting vibration. Scissoring means the vibration is like the movement of scissor. This is an in-plane blending vibration. Two atoms approach each other and bond angle decreases and increases. This is scissoring vibration, means they come close to each other. Here the bond angle is decreased and increased. And rocking, movement of atom take place in same direction. This is in opposite direction. They are moving towards each other or away from each other. But here the movement is in opposite direction, take place in same direction. Means it is going upward, it is also going upward. And this type of vibration is called rocking vibration. And outplane bending have two types: wagging and twisting. Two atoms move to one side of the plane. They move up and down the plane. I mean, two atoms, they move out of the plane at the same time. And twisting, one atom move above the plane and another atom move below the plane. One atom will move above the plane and other atom will move below the plane. In IR spectrometers, two types of spectrometer are used in IR spectroscopy. In IR spectroscopy, the two type of instrument are dispersive type infrared spectrometers, and the second one is FTIR, which is called Fourier transform infrared spectrometer. So first we will study about dispersive infrared instruments. These are older. The older IR instruments were almost always dispersive double beam designs, and the modern instruments are FTIR, Fourier transform infrared spectrometers. These dispersive instruments were often the double beam in time variety, mean they were same as double beam in time spectrophotometer, except that the location of the cell compartment with respect to monochromator was reserved. We will see here the position of the cuvette or cell compartment. These are the lamps, source lamps. Radiation from the source lamps fall in IR instruments. The radiation from the source directly fall on the sample cell, and here is only a shutter. If this part of the shutter comes in between the source and the sample, no radiation will fall on the sample. But when this part come in between the source and sample, radiation will fall on the sample. So this is the IR source. From the IR source, radiation will fall on the sample cell. This is also called cuvette. And then after the sample cell, here is the monochromator. This is a lens. Radiation will fall on the entrance slit of monochromator. This hole is monochromator. Inside the monochromator, we already studied the monochromator has a part diffraction grating. So diffraction grating will disperse all the radiations, and these radiations will be detected by photodiode array, and we have already studied about the photodiode array. Photodiode array detect multiple wavelengths at the same time. These tungsten lamp or deuterium lamp, these are used in UV visible spectroscopy. In IR spectroscopy, a hot sample, a hot solid material will be used as a source of IR radiations. In most UV visible instrument, the cell is located between the monochromator and the detector. We have previously studied UV visible instruments. In all UV visible instruments, first there is source lamp, then there is monochromator, and after monochromator is sample cell, and after sample cell is detector. But in IR dispersive instrument, there is difference. There is first sample cell, and after the sample cell is monochromator. Dispersive, this is actually not monochromator, this is dispersive part. It has diffraction grating, and diffraction grating will disperse all the radiation which are coming from the sample. Okay, in UV visible instruments, why monochromator is placed before the sample cell? To avoid photo decomposition of the sample. Here is a sample, and monochromator, and then lamp. Radiation first fall on monochromator and then fall on the sample cell. Why? Because when UV radiation, visible radiation, they directly fall on the sample, photo decomposition in the sample take place. Means the solution here can be sensitive to the radiation, and photo decomposition, the decomposition due to radiation, can take place. But in IR spectroscopy, radiation directly fall on the sample, and after the sample is wavelength selector. Because IR radiations are not very much energetic radiations, they will not cause the photo decomposition of the sample. So in UV visible spectroscopy, why monochromator is placed in between the source and sample? To avoid the photo decomposition of the sample. Note that photodiode array instrument avoid this problem because of the short exposure time of the sample to the beam. It is about UV visible spectroscopy. Photodiode array in UV visible instruments in which photodiode array is used. Photodiode array will avoid the problem of photo decomposition, because when photodiode array is used, there is less requirement of exposure to radiation. Only the sample is introduced to radiation for only small amount of time. So there will be no photo decomposition in case. This is all about UV visible instruments. Uh, Here is the explanation about IR dispersive instrument. IR radiation in contrast is not sufficiently energetic to bring about photodecomposition. So radiation will fall directly on the sample. Here is no monochromator. Also, most samples are good emitters of IR radiation because of these factors. Most samples are good emitters of IR radiation means sample itself will emit IR radiation because most of the material in the universe they emit IR radiation. Both because of these factors, the cell compartment is usually located between the source and the monochromator in an IR instrument. Cell compartment is located between what? Between the source and this one is monochromator. Thus, IR sources are heated solids. In case of UV visible spectrophotometers, lamps are used, deuterium lamp, tungsten halogen lamp. But IR sources are heated solids. Usually, any black solid, they are emitting the IR radiation, and IR detector respond to heat rather than to photons. The detector used in IR spectroscopy, it responds to heat. Furthermore, the optical component of IR instruments are constructed from polished salts such as sodium chloride or potassium bromide. We have previously studied that all type of glasses will absorb IR radiation. So in IR instrument, no glasses are used. In place of glasses, the optical materials are made up of halogen salts like sodium chloride, potassium bromides.